Hey, I'm Shania. I watched the public lecture by Dr. Riza Walsler from Stanford on dark matter and the structure of the universe. So the big idea that she walked through was basically that dark matter is everywhere. We cannot predict where it will be. We don't. We have not directly detected a single particle of it, but we can infer from various data that it's there. So the whole talk was about how astronomers got really confident about something they cannot see. So she built the case for dark matter from a bunch of different angles because, for example, the galaxy rotation curve. So she was saying that the velocity of an object um, is same whether it's on the outer edge of orbit or on the inner edge orbit. So it basically she's saying that if you go further into the orbit, your speed should drop off the farther you go because gravity falls off with distance squared. However, the speed closer and further is basically the same, and that would only make sense if there's a huge amount of mass that we cannot see surrounding the galaxy like in a halo. And then she went to gravitational lensing, which is when a light from distant galaxies bends around a massive object and we can trace this way where the mass is. And so the curves that you get show way more mass than what we can um, physically see, like in the visible stars and gas. And so another thing was that the two galaxy clusters collided, and the hot gas stuck in the middle from the collision, but the dark matter just passed through both clusters and kept going. So it didn't stop or like it just passed through it, and that's basically a direct. It shows that dark matter does not act the way normal matter acts. So that was interesting to me because I've been really interested in, space, etc. I did a lot of programs that were for the um, uh, exploration of space, and also I'm an electrical engineering major with thread and signals because I'm really curious how we can handle this much amount of noise, and that a lot of things in astrophysics are about kind of figuring out what you have to do with your data to clean out all the noise and get actually valuable data. And what was interesting to me because of this, something that I learned was that the direct detection experiments, that they are actually people are trying to detect dark matter, and the way they do it is they take a xenon gas, like a noble gas that wouldn't react with anything, and they put it really deep into the into like deep into Earth, and then you just wait. So the hypothesis is that if dark matter is a WIMP, which is a weak interactive massive particle, then once in a great while it will smack into a xenon nucleus, and you'll see a tiny flash of light or a tiny ionization signal. So the current leading experiment is Lux Zeppelin, and they use around 7 tons of liquid xenon, and um, it really interests me how they handle all this contamination because they have to check every single part, like steel and bolts, for contamination because otherwise the experiment will get ruined. And what's exciting to see is that right now this is an actual like human effort to see dark matter. So we have come to the point where we have all these hypotheses, and now we really try. It's worthy to try to see whether it actually exists. And yeah, so I think it's interesting. I love signal processing and all of that stuff. So you should watch the talk.